Why is the computational basis key to Grover's algorithm? Imagine trying to find a single book in a huge library. Now picture doing this with a quantum computer that can look at all the books at once. That's what Grover's algorithm does. But to understand how it works, we need to look at the foundation it relies on, the computational basis. Think of the computational basis as the standard language of quantum computers. It's a set of basic states, each representing a specific item in a search space, like a unique book in our library. These states are written as X, where is a binary string that encodes the item. When we set up Grover's algorithm, we start by putting the quantum register into an equal superposition of all these basis states. This means every possible item is represented at the same time, allowing the quantum computer to process all options simultaneously. The oracle, a special part of the algorithm, is designed to recognize the correct item. It does this by flipping the phase of the basis state that matches the solution, changing its sign while leaving others untouched. This phase flip only makes sense in the context of the computational basis because it directly targets the specific basis state that encodes the answer. After the oracle marks the solution, the diffusion operator kicks in. It amplifies the probability of the marked state by reflecting the entire superposition about the average amplitude. This step also depends on the computational basis because it manipulates the amplitudes of all basis states directly. When the process repeats, the probability of measuring the correct item increases. Finally, when we measure the quantum state, it collapses back into one of the basis states, revealing the answer. Without the computational basis, the oracle wouldn't know which state to flip, and the diffusion process wouldn't have a clear target to amplify. From a quantum information perspective, Grover's algorithm uses the structure of the computational basis to perform searches faster than any classical method. It does this by coherently manipulating the amplitudes of these basis states, boosting the chances of finding the right item with fewer steps. This makes Grover's algorithm especially useful for searching unsorted databases or solving problems that can be turned into unstructured searches. The computational basis is the language that allows the quantum computer to recognize, manipulate, and amplify the correct solutions efficiently. In essence, it's the fundamental framework that turns the power of quantum mechanics into a practical search tool.